So we would like to discuss here the normal force and related frictional forces. So generally speaking, these are contact forces between surfaces, and the normal force is the part that is perpendicular to the surface, say between two objects, and frictional forces are typically parallel to the surface. So if I had, for instance, some box here on my flat surface, then there might be a force perpendicular, which is the normal force, and there might be, if there was some, say, applied force in this direction, then there might be, between the surface, there might be, for instance, some frictional force here that was in the opposite direction. And so the frictional force here is the part that's related to how the surface and the box here are the part of the force that's parallel to the surface, and the normal force is perpendicular to the surface. So now, typically, we need to find the normal force in order to determine the frictional force, because the frictional forces are frequently mu times the normal force in magnitude. And so we tend to break up the frictional forces into two categories. We might have the static frictional force, and we might have the kinetic frictional force. And in the static frictional force, there's no slipping between the two surfaces, and in the kinetic frictional force, the object is slipping across the surface. And so typically we use little f's for frictional forces, and we say that the static frictional force is always less than or equal to the coefficient of static friction mu sub s times the normal force, and the kinetic frictional force is always equal to exactly mu sub k times the normal force. So we'll get to some opportunities to compute the static frictional forces in a moment, but first let's just think about the normal force. In the typical problem, for instance, the one that we have drawn, we might also have some force of gravity here pulling downwards. We would need to define some coordinate system, and I might choose plus x to the right and plus y to be vertical. And then we would solve the sum of the forces is equal to ma as a vector statement, would become the sum of the forces in the x direction is the mass times the acceleration in the x direction, and the sum of the forces in the y direction is the mass times the acceleration in the y direction. And what I've done in the way I've organized my forces and my directions, I see that here, when I added up the forces, I would have the normal force minus the force of gravity. So in this case, I've arranged my y component of the forces to have the normal force in it. And typically what's going to happen is that the normal force will adjust to hold the acceleration equal to 0 in the direction the normal force points. If the object is not, say, accelerating in that direction. So that's a fairly typical scenario. It's not the scenario if we're moving in circular motion through a hill, but that would be a fairly typical scenario that would apply, say, here to this box. And so in that case, I would say that the normal force minus the force of gravity is equal to 0, and that would allow me to say that the normal force is equal to the force of gravity, and the force of gravity is, in this case, is mg. And then if this box was, say, moving, let's say the box was moving to the right, then I would know that the frictional force in that case would be the kinetic frictional force would be mu kinetic times the normal force. And since I've now found that the normal force is equal to mg, I would say that the frictional force is mu kinetic times mg, where mu kinetic is going to be some number, something like 0.2. It doesn't have any units. It's a fractional relationship between the strength of the normal force and the strength of the frictional force. And so now if I took the sum of the forces in the x direction and I look back at my figure, I would see that there was the applied force minus the frictional force was equal to the mass times the acceleration in the x direction. And so whatever the applied force would be, I would then subtract off mu sub k mg, because I've determined that the frictional force is mu sub k mg. That would be equal to the mass times the acceleration in the x direction, and then I could solve for whatever it is that I wanted to solve for. And so this is the sometimes typical case in which the normal force is equal to the weight. But the normal force, it's important to recognize, is frequently not going to be equal to the weight.